Okay, thanks. This is a bit of a diversion from what's been talked about and what will later be talked about, but I'm going to introduce the group really because I'm not doing any science. I'm just telling them what we ought to do. And they'll give their talks afterwards, which deal with the science. But I thought I should perhaps give a bit of a background for what Metal Oceans is and what we're trying to achieve. It is the brainchild of a bunch of people who said, you know, people have been studying and looking at comparisons between greenstone belts and modern oceanic crust forever, but we haven't really been keeping up with the research that's being done on the ocean today and how much we actually know about modern ocean crust today. So that's really the crux of the Metal Oceans project, is to try and get greenstone belt understanding up to par with what we understand for modern oceanic crust. And in particular, to challenge some of the thinking about, for example, back arc basin formation, which traditionally has been a very simplistic model and, as it turns out, is very complex. The group is huge. It's a combination of people here in Canada and people overseas. And these people are all making geological maps. That's the activity of Metal Oceans, is to make geological maps of the ocean floor in places where we don't have any maps. And these people have become really global experts in integrating marine geophysical data with geological interpretation of crustal growth in the oceans in ways that have never been done before. The support for the project, of course, is underpinned by Metal Earth, but because of some of the activities that we're involved in, which include going to sea, it's quite costly, and so we have big partners that include the German Marine Research Institute in Helmholtz, Geomar, and now more recently an Image Create project, which is providing some of the training that we need to get students in the position where they can contribute to the geological mapping. Our goal is exactly the same as everybody in this room, and that is to better understand the relationship between metal endowment and crustal growth in particular. We recognize for all mineral deposit types really the strong correlation between the abundance and distribution of ore deposits in episodes of crustal growth. This plot here shows VMS deposits of different types through time. And you can see that there's a very strong correlation between the abundance of deposits and these episodes of crustal growth. In the Abitibi, 85 VMS deposits in the Abitibi, they form within a very narrow 30 million year window. What is the signal? What is the characteristic of those pulses of crustal growth, and how can we recognize them in the Abitibi and in other greenstone belts? We chose as an area in which to test some of the ideas the outer margin of the Indo-Australian plate. This is some of the fastest growing crust on Earth, highest inferred mantle temperatures on the planet. Major mineral endowment, not only on the modern seafloor, hydrothermal vents in the Lau Basin, the Fiji Basin, the Bismarck Sea, but also, of course, major copper-gold systems, at least 3 of the top 10 copper-gold systems in the world. And so this is our study area. We're zoomed in mostly within the last couple of years in the northeastern part of the Lau Basin. There's an outline there of the Abitibi Greenstone Belt tipped over on its side and shown for scale. And the questions that we're trying to address here are basically the same questions everybody here is trying to address. What do those pulses of crustal growth look like? And can we recognize them in different greenstone belts? What are the probable time and space scales? How fast do things happen? And over what distances? And can we recognize certain things like mantle anomalies that may be associated with short bursts of crustal growth? And increasingly, as you'll hear from Alan in a minute, what types of ancestral structures could have controlled mineral endowment, not only VMS deposits, but also later orogenic gold. The starting point for the project really was the construction of this map, which was published by the Geological Society of America a couple of years ago now. Meg was leading that project, but it was a team of hundreds who were building this map. And it's a unique contribution to the understanding of the geology of the modern oceans because it's the first time anybody has tried to create a lithostratigraphic assemblage map of a marine environment. And we were able to do this, at least we think we were able to do it. We got it published. And it comprises a very complicated history of the northern part of the Lau Basin and the southern part of the Lau Basin, made up of about 40 different geological formations and about 30 different assemblages that were reconstructed in over a time period of about 30 to 40 million year period. So in fact, this is the 30 to 40 million year window that I alluded to earlier with respect to the Abitibi VMS, for example. So we're going to look a little bit about that, but I can't understate the impact that this map had on the research that we're doing. Everyone in my group is looking at this map on a daily basis to guide the questions that they are asking and trying to test. We performed our own experiments in the Northeast Lau Basin. This is an example of a close-up of the northeast corner of the Lau Basin, which comprises an active volcanic arc, shown here. It comprises an incipient back arc rift, and then a large expanse of back arc basin crust that grew over a period of about 3 to 5 million years. The experiment that we designed was basically identical to a metal earth transect, which was to combine reflection seismics, seismic refraction, gravity, magnetics, heat flow, magnetotellurics, geological mapping using underwater autonomous vehicles, sampling, geochemistry, geochronology, basically everything that you can possibly do in a marine research environment we tried. And the difference between what we did and what many other researchers have done is that, well, we only had a limited amount of time, so we did everything at once. And we did that with a huge amount of help from our colleagues overseas on a major research expedition over a period of about 2 months. And we had at least 39 people engaged in performing all of those tasks. One of the major tasks was about 1,000 kilometers of seismic reflection, which was performed using a 4-kilometer streamer. That's science streamers. Oil and gas streamers are like 10 kilometers long. Unfortunately, we can't have access to that. To insonify the crust across that arc to back arc transition. This is our version of a thumper truck. These are 12 air guns that are pumping air into the water column at about 85 liters at a time every 20 seconds, weeks on end. I can tell you that after the first few days, the novelty of that sound coming up through your legs and into your spine kind of wears out. The seismic reflection data produced about 25,000 shot points. And then we turned around and did the whole thing again using deployments of ocean bottom seismometers. And this allows you to get at the deep crust. So the seismic reflection will give you top 7 kilometers. The OBS data will give you down to the MOHO, 20 kilometers at least. These are the seismic sections, which are about 100 kilometers apart, stretched out over about a 500 kilometer length of the arc to back arc transition. As I said, we get seismic reflection data up to about 7 kilometers deep, and then refraction data, which I'll show you a little bit later, down to 20 kilometers. With that much data, you have no choice but to basically wallpaper the inside of the ship and spend weeks on end arguing about it while you're at sea. We were surprised by one thing, and I think that was the complexity of the back arc crust. We had all visions of a single back arc spreading center forming continuous and monotonous back arc basin basalts. It's nothing like that. And this is something that I think we need to carry into our understanding of greenstone belts as well. We had, for example, this is one of the sections, just the seismic reflection data, a huge region of arc rifting ongoing with arc extension ongoing with arc rifting, huge blocks of arc crust stranded way out in the middle of the back arc basin, and sedimentary basins throughout the back arc basin that are being continuously intruded by melt. This is not what we expected over a 300 kilometer strike length or a 300 kilometer cross section of the back arc basin. The amount of melt in the back arc that is younger than the than the crust on which it occurs was astonishing, and we had hundreds of cubic kilometers of melt in the form of small volcanoes throughout the back arc basin. Here's the currently active rift. This is the older back arc basin crust, and you can see all of these tiny little dots are 1 to 2 to 3 kilometer diameter volcanoes on that old crust. Basically, recording the wake of the back arc spreading center as it migrated from west to its present position in the east. Not only volcanoes, but an incredible number of what I would consider to be not too small sedimentary basins, 20 kilometers, 30 kilometers in strike length, hundreds of meters of volcaniclastic material, all of different age, recording the spreading, the extension, the distributed extension between the back arc spreading centers, the multiple back arc spreading centers that exist in the northern part of the Lau Basin. In addition to the seismic reflection, we collected about 4,000 kilometers of towed magnetics, continuous gravity from the deck of the ship, and for 40 days we had electromagnetic sensors deployed at the spreading center itself to measure the resistivity structure of the crust. As I said, nobody's really done anything like this before. The magnetic data was, like everything else, a surprise. We expected wonderfully linear magnetic stripes like you get on a mid-ocean ridge. We got nothing of the sort. We got magnetic chaos in the immediate back arc basin with some fabric which is at a high angle to the east-west opening of the basin. This, we suspect, is a reflection of the microplate rotation, which we're going to hear about from Alan in a moment. The gravity data allowed us to look at crustal thickness and mantle topography, which Chris is going to talk about in a few moments. I'm not going to talk about it. We even did, as I said, magnetotellurics, and this is really the cutting edge, because nobody's ever tried anything like this in a modern back arc basin that's currently active. And what we found at the tip of the spreading center, the currently active spreading center, are low resistivity zones that extend down to at least 5 to 10 kilometers. And I'm struck, this is Taus's map or section, MT section from Noranda. I'm always struck by the similarity in the geometry of those anomalies. I don't have any idea what that means, but there they are. We're pretty sure, in fact, we're not sure, we know for certainty that this particular anomaly is related to an intense zone of active seismicity and probably either hydrothermal fluids or melts. This was the main goal or the main outcome, I think, of the geophysics, which was the crustal velocity data from the OBS measurements from the refraction data. And what it shows is the position of the MOHO underneath the back arc rift and the other edge of the Nuafo'o microplate, which I'll show in a moment. We expected a mantle upwelling like this, this feature right here, immediately under the Fonolai rift. What we didn't expect was about 150 kilometer wide zone of mantle upwelling, which extends all the way from the back arc spreading center, all the way from the edge of the Nuafo'o microplate, almost all the way to the other side of the Nuafo'o microplate, which is bounded by this major crustal scale shear zone. What it suggested to us is that the things that we map at the seafloor and the things that were mapped in our geology map of the Lau Basin are really mapping out mantle domains. This is a close-up of the OBS data, the seismic tomography. There's the mantle upwelling under the Fonolai rift. There's this 100 to 150 kilometer wide zone of mantle upwelling, which coincides with the Nuafo'o microplate. In addition to that, the internal complexity of the crustal velocity model was also a little more than we expected. You can see huge zones that are several, 5 to 10 kilometers wide of something. So as I said, all of this is actually recorded in the original map that we made at 1 to 1 million scale. And we're principally looking at the two distinct areas of the Lau Basin. The northern Lau Basin, which is dominated by a series of back arc spreading centers, which I'll show in a minute, and the southern Lau Basin, which is really just one long back arc spreading center. That's what we expected. That's the norm, or at least that's what's in everyone's imagination of a back arc spreading center. Separated by this purple blob, I'll show you in more detail in a moment, which is the Peggy Ridge transform. And this is a fundamentally important structure that Alan will talk about in a moment regarding the origin of the microplates within the northern part of the Lau Basin. The outstanding outcome, or the outstanding feature, is that the extension, the hyper-extension that's occurring in the northern part of the Lau Basin is really due to not just one fast-spreading center like we saw in the southern Lau Basin, but at least a dozen. And they're all operating at the same time, and they're all contributing to the opening this distributed extension, the opening of the basin. And interestingly, because there are so many of them, they can accommodate that extension by opening slowly. So they're slow spreading centers. They're all slow spreading centers, the cumulative length of which is greater than the much longer eastern Lau spreading center in the south. So effectively, many short, slow segments are doing the work of one long, fast segment. Meg put all this into the context of assemblages in the northern Lau Basin, different colors. I think Alan will also show a version of this. The youngest assemblages are shown in pale green here. There are about 9 of them that formed within the last 5 million years. But the whole history of the Lau Basin records, based on area-age relationships, records an early, relatively low, slow growth, followed by a surge of crustal growth at about the time when Peggy Ridge first appeared. Peggy Ridge being the large transform fault, the conveyor belt really, that allows that extension to occur in the northern part of the Lau Basin. Alan's going to be talking about this crustal burst up here, but essentially in the early history of the back arc assemblage, we're looking at about 3,500 square kilometers per million years of crustal growth, and then a sudden jump to about 9,000 square kilometers per million years. That pulse of crustal growth is really what we're interested in exploring in more detail now, and that's what most of the guys are doing. We thought that maybe this was a microplate map. We thought, this must be our map of the microplate breakout caused by the collision with the Melanesian border plateaus. But it turns out that the assemblages are not microplates, and I believe this is also a lesson that will be quite useful going forward, even in the Abitibi. In fact, the microplates are structures. Assemblages are lithostratigraphic subdivisions, and the microplates are structures. They're not the same thing. If you want to map microplates, you have to map the overlapping spreading centers, you have to map the propagating rifts, you have to map the shear zones, you have to map the fracture zones, all of the things that could be the boundaries of the microplates, which Alan will talk about a little bit later. If you stitch all of those structures together, you get what looks like a microplate map. In this case, it only shows, I think, 7 in here. I suspect that there's a microplate in here, and a microplate in here, and a microplate in here. There's probably a dozen microplates, or sometimes we use the word nanoplate, as little as 100 kilometers across. Alan does not like this slide because it gives the impression that the microplates are rigid features and that they are continuous. They have a continuous boundary. He'll explain why he doesn't like it in a minute, but I'm the boss, so I get to show it. If you take the microplate map on top and put it on top of the assemblage map, you can quickly see the difference between what a microplate is and what an assemblage is. And the bottom line is that microplate boundaries are effectively bisecting assemblages. So here's a good example. In the background is the Phonolai assemblage, this gray triangle here. And you can see that the boundary of the microplate runs right down the middle of the assemblage. Half of the assemblage is on the Tonga microplate, and the other half of the assemblage is on the Nuufo'o microplate. And in fact, all of these assemblages are made up of many slivers of crust of different ages. So the assemblages and the microplates are very different things. Recognizing assemblages, of course, is easier in greenstone belts because all you need is the age and the geochemistry, and the structure is something you worry about later. In the modern ocean floor, we're doing it the other way around. We're very much focused on trying to understand the structure. And one of the hallmarks of microplate formation, in fact, it's a requirement of microplate formation, is the formation of triple junctions. Every microplate that forms, every plate that fragments, forms at least two triple junctions, at least two triple junctions. And so we're beginning to now trying to understand what is it that these triple junctions actually look like, and could we actually start to see them in the geological record. Aaron, who's here, has been doing, maybe machine learning is going to help. I think we're going to hear from Jeff later about something like this. Aaron has been doing triple junction density maps, heat maps of triple junction density to show where they occur and to take advantage of the data sets that are available. And you can see that the hot spots really correspond to the triple junctions that we've already mapped out. One of the questions that we're interested in now is what happens if we take a terrain like this and you shorten it by a factor of 2 or 3. And in my mind, I think it starts to look like a greenstone belt. In the case of the Abitibi Greenstone Belt, we're only dealing with 7 assemblages, or maybe people think there are more now, but I suspect that there are many more microplates. And in fact, we go from a situation where we have a high angle fault intersections, which is what Aaron was mapping, to a sinuous network of low angle fault intersections. This burst of crustal growth in the northern part of the Lau Basin, or this proliferation of assemblages, is actually coincident with what we're now calling peak microplates. So it's a time period in the evolution of the Lau Basin. We don't know where it's going to go in the future, but Alan, I think, is going to maybe mention that. But at this particular time, we're at the point of peak microplates. Maybe this is one of the reasons why VMS deposits form such a narrow stratigraphic interval within greenstone belts relative to the whole time period required to assemble that terrain. So other people in the group are taking a closer and closer look at triple junctions. We've come down from 1 to 1,000,000 scale down to 1 to 100,000 scale to map some really spectacular triple junction boundaries in different parts of the Western Pacific, and trying to look at things at the same scale that we might recognize, for example, in the southern Abitibi. And we're now moving forward with that. I would say this is one of our objectives for the next. How many years have we got? 4. In addition to the structural analysis that Alan is doing and the work that Aaron is doing, Mark Fassbender, who's here and will be talking, did a spectacular job of assembling data from the Lau Basin on the geochemistry of the volcanic rocks. This has only been possible really in the last decade because of the intensity of sampling that has taken place. And like everything else we've seen is an unbelievably complicated and variable chemistry of the back arc basin crust, including arc-like rocks, mid-ocean ridge-like rocks, ocean island basalt-like rocks, all within 100 kilometers, sometimes even 10 kilometers of each other. And Mark will talk about that in a moment. One thing that I'm quite interested in is can we link that to things that are going on in the mantle? And the one thing that's particularly important about the Lau Basin is that it is associated with a massive mantle plume in the water column. In other words, a helium plume from the mantle in the water column, and also recorded in the basalt glasses in the northwestern corner of the Lau Basin, at least, that record mantle contributions or mantle input into this dynamic, this very complex dynamic that I've been referring to. And this is something that we want to explore in a little bit more detail. In particular, we want to explore the structural and the petrological indications of these processes, because we think that this is probably related to endowment. So just some immediate outcomes from the last, I guess, 3 or 4 years on the Lau Basin. The very first message is that the Lau Basin did not form by a continuous process of back arc basin opening and accretion like we would expect, maybe in the south, but certainly not in the north. Rather, it originated from episodic combination of repeated arc rifting and ridge jumps and widespread intraplate intrusions and distributed extension. I think this complexity is actually what a pulse of crustal growth looks like, and the product is neither entirely oceanic nor entirely arc-like. And it's the intense deformation of the microplate mosaic that likely explains the abundance of magmatic and hydrothermal activity in contrast to some other much simpler back arc basin environments.